MIMO system. Okay. So here is the hardware. You can see that we have this helicopter model. This is a helicopter model, laboratory size helicopter model. Okay. Just like the helicopter, we have two rotors, the main rotor and the tail rotor. Okay. So when this main rotor rotates, the thrust generated by it gives the pitch angle, and the tail rotor thrust gives the yaw angle. Okay. So we have this setup has 2 degrees of freedom, right? The pitch angle and the yaw angle. Okay. So what we will do in today's experiment is first we will model the system, find out the transfer function model, and then design a PID controller. Alright. So this TRMS is a nonlinear model. You have seen the dynamic equations. They are in the nonlinear form. The state space equations are in the nonlinear form. Right? So while designing the state space model, we have assigned 6 states, isn't it? One for pitch angle, another for yaw angle, then 2 corresponding angular velocities, pitch angular velocity and yaw angular velocity, then the thrust generated by these rotors. So these are the 6 states, and the 2 inputs are the voltages given to the main rotor and the tail rotor. Okay? And we have chosen the pitch angle and the yaw angle as the outputs. Okay? So we have 2 inputs and 2 outputs. So it's a MIMO multiple input, multiple system, multiple output system. Okay? So that's how we have the MIMO in this. It is not a SISO, it's a MIMO system. Okay? So we have got the nonlinear state space model, but we are going to use the PID controller to for its outputs to track the reference trajectories. So the pitch angle and the yaw angle, as you know, are the outputs. So we will give reference trajectories for these outputs, and the control objective is for the output to track these references. Alright. So to meet that, we will design the PID controller. So as if we are using the PID controller, we need the linear model of the state space or the transfer function form. Alright. So from the nonlinear model, using the Jacobian, we will find the linearized state space model first, and from the linearized state space model, we will obtain the transfer function form. Okay? So as I said, it is a MIMO system. This transfer function is a transfer function matrix, not just a scalar element relating the input and output. So as you can see, we have a 2 cross 2 matrix, transfer function matrix. Alright. So if y1 and y2 are the outputs, pitch angle and yaw angle, and the corresponding inputs are u1 and u2, y1 will be equal to g11 times u1 plus g12 times u2, right? And y2 will be g21 times u1 plus g22 times u2, alright? So as you can see, other than the g12 element, all the other elements are present, right? So u1 and u2 affects both y1 and y2, right? So there is coupling. It is not just u1 affecting y1 and u2 affecting y2. So to decouple this matrix, we would use the decoupling method. Right? So we would pre-multiply the transfer function matrix with the decoupler, so that we get the decoupled form of transfer function matrix. So the matrix and decouple the transfer function matrix. Alright. So once it is decoupled, we won't have the off diagonal elements. Right? That means we will have only the diagonal elements. The off diagonal elements will become 0. Right? So now we have the decoupled form of the transfer function matrix. Right? So y1 will be related will be g11 times c1, and y2 will be g22 times u2. Okay? So we have the decoupled transfer function matrix. Now we will go forward to design the PID controller to meet the control objective. Alright. So first part is simulation. So we will consider the g11 and then find the open loop and closed loop responses. Alright. Similarly, after that we will do the open loop and closed loop response of g2. Alright. And we will ensure that the PID controller design meets the control objective. So with these PID values, you can observe the scope therefore the step input is being tracked by the pitch angle. Similar to the step response, for the sinusoidal response, these are the Kp, Ka and Kd values. By choosing these Kp, Ka and Kd values, you can see the response as given in the figure. The same will be repeated for the yaw angle. So we will open the software and the MATLAB file for the corresponding hardware system will open up. Which is yours, of course. So in the hardware we have the twin rotors, the main rotor and the tail rotor. So the encoder and decoder are present in this hardware setup. The encoder measures the pitch and yaw angle. So for control we need to measure the outputs so that we can compare the output with the reference trajectories. So we need to the control objective is for the pitch angle and the yaw angle to track the reference trajectories. So as we are using PID controller, we need to generate the error. For that we need the actual output. So pitch angle and yaw angle are measured by the encoders and they will be compared with the reference trajectories and the error will be generated. And this error is given to the PID controller and it generates the control input. Right? So the digital signals generated by the system needs to be converted into analog form, amplified and given to the hardware. Right? So we have the digital to analog converter also present. Alright. So we will see the setup. It will take some time to load. You can start. So we have the TRMS simulation as well as the real-time model. So here we have the TRMS simulation model. So before we implement any controller, it is mandatory to simulate the controller with the state space or the transfer function model and verify its response and then implement it in the hardware. So we have the simulation model available over here. So the first one over here is the TRMS nonlinear model. It is an open loop model of the TRMS setup. So here we have the nonlinear model of the TRMS setup and we have the inputs to be given to the pitch and yaw angle. So there are switches to select between sinusoidal and step inputs. So here we will select the sinusoidal input for pitch and step for the yaw angle. So if you run the file and observe the responses, the open loop responses do not meet the control objective of tracking the sinusoidal and step inputs, just like we observed in the simulation earlier. So now we will try turning off the input for the yaw angle. So if you make the final value also as 0 and run the file, even though we haven't given any input to the yaw angle, due to coupling there will be some effect of it on the system. Alright, so that's what we can observe from the nonlinear model. The next one is the pitch control of the TRMS setup. So here we have the reference for the pitch angle. So we can select this reference. It's a combination of sinusoids. One of frequency 0.1, another sinusoid of 0.05 and one of 0.02 with an offset of 0.4. So this reference is given to for the output to track it, and the output is compared with this reference and error is generated. The generated error is given to the PID controller, which based on the Kp, Ka and Kd values generates the control input and is given to the system. Now we can run the file. And if you observe the output, you can be seeing that the dashed blue line being the reference and the black solid line being the actual output. The output is tracking the reference. Similarly, we can simulate the yaw control. Here, instead of the reference being given to the pitch angle, reference is provided to the yaw angle. Similar to the previous case, the PID controller generates the control signal based on the error provided to it with the parameters of Kp, Ka and Kd. If you run the file, we can observe the yaw output here. Here also the reference is being tracked by the output. The next one is the 2 degree of freedom control, where we control both pitch and yaw angles. So here we have references for both. So here the pitch angle tracks the reference input, and here the yaw angle tracks the reference input. So now we can see the hardware demo of the TRMS setup. So for that we'll open the real-time model, and first we'll see the pitch control of TRMS. So as was mentioned earlier, an encoder is present to measure the actual pitch angle. So that pitch angle is compared with the reference, and the error generated is given to the PID controller. The PID controller, based on the Kp, Ka and Kd values, generates the control signal. That control signal is given to the DAC, which sends the amplified analog signal to the hardware setup. Alright, so we can run the file. So we have this start and stop buttons. So once it starts running, we can click on the start button. So we can see that the pitch is very varied. You can observe that in the scope. So the first graph gives the control signal, and the second one gives the output. So the solid line is the output, and the dashed line the reference trajectory. So even if we give some slight disturbance, you can observe that the reference is still being tracked by the output. Now we can move on to the yaw angle control of the TRMS. We will open this file. Here the reference is given to the yaw angle, and the output from the encoder is given for comparison to generate the error. The generated error is converted into the control signal by the PID controller based on the Kp, Ka and Kd values. And this control signal generated is given to the DAC and provided to the tail rotor. Once we run the file, we can observe the control action. So in this case, only the yaw rotor of the tail rotor is actuated. And if you observe the scope, you can see that the output tracks the reference with the control signal as shown here. Even here, you can give a slight disturbance to the yaw angle. Even that is being overcome by the control action. The final case is the 2 degree of freedom control. Is everyone understanding what I am doing? Right, so we will open the 2DOF file. So here separate inputs, references for both pitch and yaw are given, and the errors generated for each of these, and the different PID controllers generate the control signals required for the actuation of the main rotor as well as the tail rotor. So if you run the file, we can see that both the outputs will be tracked. Since both the references will be tracked by the outputs. So that can be observed in the scope over here. So the first one is the control signal given to the main rotor. The second graph is the pitch output tracking the reference, the solid line being the reference. The third graph is the yaw control signal, and the fourth graph we can see the yaw angle output, the dashed line being the reference. Here also side disturbances are being overcome by the PID controller. For some time it will overshoot, but afterwards it will come back to tracking the reference.